Dear learners, welcome to video on antenna field regions. In this video, I will explain antenna field regions, how the space surrounding an antenna are classified. Let us see how the field regions are classified. As we know that antenna is a radiating device which is used to radiate electromagnetic waves into the free space. Once the radiation accomplished using an antenna, there is a space surrounding an antenna. Generally, the space surrounding an antenna are divided into three regions: reactive near field region, radiating near field region or Fresnel region, far field region or Fraunhofer region. These three regions are surrounding an antenna. We are going to see how these regions are classified. Generally, we consider the boundary which are used to separate the regions. These boundaries are not unique. It is varying with respect to the dimensions of an antenna and the operating frequency. First, let us see reactive near field region. We consider an antenna with the largest dimension V, which is placed in the center of the spherical coordinate system. Once the radiation is accomplished using an antenna, the space surrounding an antenna. First region is a immediate region which is very closer to the antenna. It is otherwise called as antenna region. The region surrounding an antenna, here the reactive field components predominates. Both electric and magnetic field components are out of phase by 90 degrees. As we know that for radiation or propagation, both the E and H fields should be orthogonal to each other. The boundary of the region is commonly taken at a distance R is equal to 0.62 root of dq by lambda. For small dipole or equivalent radiator, the boundary is taken as lambda by 2 pi. In this region, the angular field distribution depends on distance from the antenna. Next, we are going to talk about radiating near field region. Radiating near field region is the region between the reactive near field region and far field region, wherein field components exist. The radiating field components but angular field distribution still depends on distance from the antenna. But there is a phase difference between the magnetic and electric field components. The inner boundary of this region is taken at R is equal to 0.62 root of dq by lambda. The outer boundary of this region is generally taken at R is equal to 2d square by lambda. So, therefore, the region exists between 0.62 root of dq by lambda to 2d squared by lambda. For small antenna, that means when d is less than 1 wavelength, the region exists between 3 lambda to lambda by 2 pi. So, this boundary is based on the criteria of maximum phase error of pi by 8. Next region is the far field region. So, in this region, where angular field distribution is essentially independent of the distance from the antenna, this region is otherwise called as Fraunhofer region. So, this region exists when R is greater than 2d squared by lambda. For small antenna, this R is greater than 3 lambda. So, in this illustration, I mentioned far field region in the green color. But there is no outer boundary for the far field region. The inner boundary is 2d squared by lambda. Here R1 and R2 are boundaries for reactive near field region and the radiating near field region. Here, in this region, both E and H fields are orthogonal to each other and also they are in phase. Next we see about how the amplitude pattern change with respect to the observation distance from an antenna. We consider this figure parabolic reflector with the largest dimension d. Once we observe near the antenna, that is in the reactive near field region, the field distribution is more spread out and nearly uniform with slight variations. Then you slightly move to the radiating near field region or Fresnel region. Once we observe that the pattern begins to smooth and form loops. And then in the far field region or Fraunhofer region, the pattern is well formed. It consists of few minor loops and one or more major loops. So from this we could understand how the shape of the radiation pattern change with respect to the distance from an antenna. So I hope that you could clear about how the field regions are classified. What are the boundary conditions for the field regions? It's very simple. For the reactive near field regions, the boundary is generally taken at R is 0.62 root of d cube by lambda. For the radiating near field region, it exists between 0.62 root of d cube by lambda to 2d squared by lambda. When radial distance are greater than 2d squared by lambda, far field region exists. Thank you.